All right, everybody. Well, it is 7:30 and time to start. If I could have maybe a couple of our presenters give me a thumbs up if they can hear me all right. All right. So welcome and thank you all for joining us tonight. I'm really excited to be here. We've got a lot of great presenters tonight. So I'm Dr. Billy Teets, and I am the outreach astronomer and also the acting director of the Vanderbilt University Dyer Observatory. With us tonight, we've got presenters again from across Tennessee and also up into Canada as well. We've got some of us here at Dyer, which is down in Brentwood, Tennessee, just south of the main Nashville campus. We've also got folks from the Memphis Astronomical Society. We've got presenters from McGill University, which is in Montreal, Quebec, Canada. The Barnard Seaford Astronomical Society is also represented this evening. And then last but not least, we have Bays Mountain Park and Planetarium joining us again. So before we start, I also want to give a little shout out to some of the folks that we have helping us behind the scenes and making sure that this runs very smoothly. A couple of my colleagues here at Dyer, Alex Rockefeller and Nathan Griffin, they're going to be monitoring the chat and getting questions over to us so that we can get them out to our presenters, and also kind of keeping an eye on things to make sure that our presentation is going out to the world successfully. And also, speaking of making sure the world sees everything successfully, we have Brian Smokler from Vanderbilt Communications. So he's the one that's really making sure that our signals are getting out to you all tonight. So without further ado, let's go ahead and jump over to our first presenter. So I'll preface by saying that a few of us have some locations that are fighting clouds tonight. So even if we do have some clouds, we're still going to have a great time. And one other thing I wanted to mention is that a lot of the objects that we're going to be viewing tonight, we have highlighted on a star chart, which you can find on Dyer Observatory's main page. So as we go through these objects tonight, you want to see where they actually are, download that star chart and then go outside and check it out for yourself. We have a nice version that you can view on your computer or even on your phone. And then we have a nice printer-friendly version that won't use up all your ink. All righty. So our first presenter is Adam Thans, who is out at the Bays Mountain Park and Planetarium. He is one of the main educators, if not the main educator out there. And he's going to be starting tonight by talking with us a little bit about, as we like to say, the star of the evening. No, it's not a star. It's not even a planet. It's a satellite. But that would be our moon. So Adam, I'm going to go ahead and turn it over to you.
Thank you very much, Billy. Yes, what I'm going to do, I'm fighting the clouds right now. So the moon's going in and out, unfortunately. So I'm hoping within the next few minutes that the moon does come out and I can show you the real thing. But let me show you a nice image of the moon that I took a little while ago, a couple months ago, but it's the exact same phase. So, you know, the moon looks like it changes over time. Well, really, it's not changing. It's just how we see the moon in the nighttime sky or the daytime sky. You can see it at both. The phasing of the moon or the different face of the moon changes because of how the sun's light is shining on the moon and how we see it, because the moon goes around the earth. And so as it goes around the earth, we're seeing more and more of it will be lit up, and then less and less. Okay, I am looking at the moon, so I am, look at that. So I'm going to be going in and out here, obviously, with the exposure and being able to see the moon. There we see the moon. This is a live image of the moon. And so right now we see what's called a gibbous phase. It's more than half, but less than full. And there it goes again. And so that is called gibbous. If it was less than half of the surface of the moon that's pointing towards us, we would call that a crescent phase, where it looks like a C shape. And as the lighting on the moon from the sun's light is shining on the moon, but as the moon travels around the earth, we're seeing more and more of it. And so that shadow line, which is the boundary between day and night. All right, I'm going to go to my backup image as we fight the clouds. That boundary line, it's actually called the Terminator. And so that Terminator is the boundary between day and night. If you were on the moon, right there at that boundary, and as the moon orbited the Earth, there would be a moment in which you'd be first in nighttime, and then the sun's light would come over the horizon and just sweep right across you. There wouldn't be twilight, like we have on Earth, because the moon has no atmosphere. There's a lot of cool features on the moon. I have this other image that hang on. Here's the real moon. Okay, so we're going to go back and forth for a few moments. So we're going to see how those craters along the Terminator there, those are caused from rocks from space crashing into the surface and making a large hole in the ground. Now, because the moon has no weather or wind or rain, those craters basically stay there almost forever. And as I keep adjusting the exposure based on the clouds, you can see some ray structure coming off of that one crater to the lower right. That crater is Tycho. And, well, there we go. All right, go back to this one. So you see that crater to the lower right, that's Tycho with the central peak. And then you see this ray structure leaving it. So that's what's called ejecta. So imagine if you had a tub full of flour and you threw a big bowling ball into it, that flour is going to go psh, and shoot out all over the place. And when it lands on the ground, you'll see these kind of lines of the flour radially outwards. And so that's kind of the same thing. Obviously, it's not flour. It is the surface of the moon. I am hoping that we can see Mars later, and I will be talking about Mars later on into the evening, but my time is up. And so what I am going to do is give my feed back to Billy so that we can go on to the next person. I want to be fair to all of them. So thank you, and I'll be back with talking about Mars.
All righty, well, thank you very much, Adam. At least the clouds cooperated for a moment, so we got a little bit of a live view there, so we'll take that. Do we have any questions? So as we're going through our presentations tonight, if you're watching from YouTube, there should be a YouTube chat there. If you've got questions, type those in, because we're going to have Alex and Nathan. They're going to be holding those questions so that at the end of our 10 to 15 minute presentations, we can then get some of those questions answered. So Alex, or Nathan, did we have any questions about the moon at the moment? So it doesn't look like we have any at the moment.
Don't believe so.
Okay. All righty. Well, folks may still be getting their questions together. Well, let's move on. So thank you again, Adam. And now we're going to come back from East Tennessee and go back towards, I believe it was Gallatin, to Theo Wellington, who is with the Barnard Seaford Astronomical Society, which is the big amateur astronomy group here in the Nashville area. She's also a JPL Solar System Ambassador. So Theo, what are we going to be looking at tonight?
Okay, so thank you, Billy. We're going to be looking at, do I need to do anything to get on the big screen or not? All right, we're going to be looking at Albireo, which is a lovely double star. And because it's hard to switch between things real quick, this is not going to be a live stretch. Later on will be live, I think. But I did this just Monday night, so it's almost live, sort of live, kind of live. But anyway, let me see if I can share my screen. And here we go. Share that. There we go. So double stars are a thing. We live by a single star, which is kind of strange. Most stars actually are doubles, some are triples, even quads. So there are a lot of different ways that stars get together. And they're pretty to look at in the night sky. So this one's cool. It's possibly a physical double. It's really wide. That's why it's fun for amateurs to look at. And because of it's so wide, we're not really sure that it's a physical double. It could just be a chance alignment. But if it's physical, it goes around each other in 100,000 years. So it's pretty hard to watch that motion. We're trying hard to resolve that by using accurate distance measurements to see if they are indeed at the same distance from Earth, or maybe they're at slightly different distances. So we're still working on that. But it's about 400 light years out, and the brighter of the pair is itself a double star. It's also one of the prettiest contrasting color pairs in the night sky. So let's see, let me go to here and down. There we go. What we're looking for is, if you look up almost straight overhead tonight, we've got the summer triangle, 3 bright stars that make this really easy to find triangle. So we've got Deneb, Vega, and Altair, and we're going to be focusing on Deneb tonight, because it's the tail of Cygnus the swan. Now I know you got to use a little bit of imagination here to see a swan, but that's the tail, long neck out to the head, and then 2 wide wings on either side. And if we do use some artistic imagination, we can actually see the swan there. All right, and what we're going to be looking at is the star that makes the head of the swan. The star's name is Albireo. So to your eye, it's 1 star, it's Beta Cygni, which would make it the 2nd brightest star in Cygnus, but it's not really. So either at some distant time it was, or we just misnamed it, because the body star and the 1 wing star are both brighter. But anyway, it's 2nd in line in Cygnus, and it's really easy to find because it's the head of that swan. So that's a nice wide field view. That would be an extremely low power view. You can just barely make out the 2 stars, but actually if you're looking at this through the telescope, your eyes will pick up the colors even better than they show here. And I like to ask people when they're at the telescope, what colors do you see? Because actually I get quite a range of answers. And there's not really a correct answer, because everybody's vision is, after all, a little bit different. So just to contrast, this is the same field of view with the moon in it. So let's get in a little bit closer. So if we were looking at the moon, we'd be this close. But that's what the view looks like through the telescope at maybe a moderately high power. So that's kind of fun. And they are a distinct color, right? All stars are dots. So one here is not bigger than the other one, even though in real life they are. But one is very much brighter than the other one, and that just makes it kind of soak into the camera a little bit better. So usually the answer is 1 star is very, very yellow, and then the dimmer star, I can get anything from purple to green. The most folks settle on blue. And I can actually amp the color up a little bit as well. Honestly, this is pretty close to what your eye can see. Now, most stars are white to our eyes at night because our color receptors don't work well at all in low light. So our eyes switch to using the rods and mostly black, white, and gray vision. You know, at a star party, I can see everybody, but I might not know what color shirt you're wearing. So what the telescope does for us, it gathers more light. And for many stars, this is just enough to see some color. Now, they're different colors because they're different temperatures. We often talk about the spectral type of a star, which also includes its luminosity or brightness information. Small stars can be cool red stars, but large supergiants like Betelgeuse can also be red because it's very cool on the surface, right? So Albireo A, the brighter one, is a K2 star. Most people see that as that lovely golden color. About 14 solar masses, so it's pretty good size, larger than our sun. 1,200 times more luminous than our sun. It is itself a double, but those 2 are so close that we can't visually split them. Now the pretty blue companion is a B8. That's a cute rotating blue star that's 3.7 solar masses and only 230 times as bright as our star. So they're both bigger and more luminous than our own sun. All right, double and even, triple and multiple stars are really fun targets for backyard telescopes. Many of them have really pretty color contrasts. Some years ago, longer than I like to think, when I started with just a 5 and dime store telescope, double stars were fun to find and a challenge to see if I could see the 2 stars. They're also often easier to see than some of the faint nebulae, even from our city with the high background light. So if you have a small telescope, check out observing lists of double stars. There are lots of cool resources like the Astronomical League's observing lists. And many stars are also variable, so that's yet another thing you can look at while you're watching the double stars. I know that the fun nebulae get all the cool press, but stars on their own are fun to observe as well. All right. So that's about what I have here. Does anybody have any questions, or I can, let's see, stop sharing that.
Yeah,
there we go.
But let's see. Yes, we did have some questions. So how close together are those 2 stars, would you expect? I know that you said that we don't know if they're an exact, an actual double rotating around, but are there any estimates to how far apart they might actually be?
There are, and I actually looked that up earlier today. It should have been there on the darn page because my brain doesn't hold that much anymore. But far apart would be a good answer. Let's see.
And so when you say far apart, would you anticipate probably farther than, say, Neptune is from the sun?
Yes, and probably several times that, because otherwise we would not see that separation. They're all, people always give the separation of double stars in how far apart in angle they are in the sky. Mm-hmm. And that's not really very interesting if you want to know how far apart are they if I'm standing there. So that is a good question. I'm not sure we know that they're far apart because of that angular separation, but it's going to depend super critically on what their exact distances are. And I'm not sure we're accurate enough to be able, somebody would know that. Let's see if I can.
Adam says probably light years.
Probably not many light years, because you get, that's going to get hard to be bound, which, that is the question as to whether they are actually a bound pair. Let's see, spatial.
I think that I think that the Gaia mission, which is out in space right now, trying to position or get to positions of over 1 billion stars, I think some of the preliminary results suggested they are not. But don't quote me on that. I think I'm remembering that correctly. But
yeah, I've seen that too. The distance is just enough that you're going, that's kind of far, and so it's probably a line of sight thing. But yeah, 34 seconds of arc, that doesn't help.
There's a question: what makes a star blue?
It's color. So just like if you think about a flame, the hottest part of a flame is in the center. So the surface temperature of the star is what its color is, essentially. So blue stars are really hot, and then a lot of times the cooler stars, they can be either cool because they're little or cool because they're so super giant and inflated that their outer layers are pretty cool. But that tells you something about their surface temperature.
Okay. Well, thank you, Theo. We had a couple of questions pop up about the moon, and we're actually a little bit ahead of time here. So let's circle back, and if we can, Adam, if you wouldn't mind answering a few of these.
Sure.
Let me find back up here.
In the chat.
Yeah.
You want me to go through?
Sure. That'd be fine.
Okay. Well, I'm sorry. I'm kind of butting in. So the moon has no atmosphere. Right. So you have to wear a pressure suit. There's no air. There's no water, rain, no animals, plants, nothing. It is essentially a dead world, the moon. And then it talked about twilight. Well, twilight is caused by the scattering of light by our atmosphere here on Earth. And so you get that slow progression of daytime to nighttime. It's not just boom, the shadow of the sun just passes over you and then it's immediately super dark and you see all the stars. There's that very gradual transition, and that is directly from our atmosphere. So it's scattering that light between the boundary between day and night. So our Terminator on Earth, as seen from space, is actually quite broad and like a gradient. It dissolves into night. On the moon, if you put really high magnification on a view and really look at the moon right at the edge there, you're going to see light like coming across a crater and hitting the top of one of those central peaks. But then below it, it's in pure black. Because it's in shadow. And if you watched probably over an hour, you would see the shadow line changing, but there is no twilight. That's an excellent question, actually. Let's see. The sun lights the moon. So the moon is about 250,000 miles. It's actually 240,000 miles away from the Earth. The sun is 93 million miles away from the Earth-Moon system. And so it is so far away that it actually takes light at the speed of light, which is 186,000 miles per second, 8 minutes to travel to us from the sun. So it's really, really far away. So the sun's light is just shining out in all directions. It is a star. And that light is hitting the moon. It's also hitting the Earth. And so if you look at a photograph from an astronaut that went to the moon, and looking back at the Earth-Moon system, or even a satellite or something, a spacecraft, you would see both the Earth and the moon with the same phase, because it's how the sun's light is shining on both of us at the same time. But we live on Earth, and so our perspective is very Earth-centric. And it's just kind of one of those things you got to think about. But the moon is the sun is shining light onto the moon as well as us, and that's why we see phases, because the moon goes around us. A good activity at home to do: hold a tennis ball on a like a tennis ball on a stick at arm's length. That's not to scale, but then have one light source, like a bare bulb from a lamp somewhere off in the distance, and then have that, you can see my arm in the background. Hold it and go, have the moon go around you as you're looking at the moon. You're going to see the lighting of the moon, your moon model, change with the phases. Let's see, very quickly, did that. I do not know when the first woman is scheduled to be on the moon. Long time coming, I'll say that. Volcanic tubes are on the moon. They're probably collapsed, so I don't think they'd be. We would be able to use them, but it is known for the moon and Mars that digging down, I think it's like 5 feet is enough. That if you had a structure about 5 feet below the surface, that it would be enough soil above you to protect you from radiation. And so a long-term base may be that they dig down or build the structure and then cover it over with dirt as a natural protection. But that's a very interesting thing to think about, and not many people do, so that's great. Someone asked about the phase. It is a waxing gibbous moon tonight. Waxing means it looks like it gets bigger, and waning when it looks like it's getting smaller. Of course, it's just more sunlight day to day or less sunlight day to day. So it's waxing, waning when we're in waxing, and then gibbous is the shape. So it's more than half of the moon, less than full.
And Adam, I had a question for you. We still got a couple minutes, and since our moon is our star of our evening, I've come across the misconception that a lot of people think that the phases are caused by the shadow of the Earth hitting the moon. Can you give us any information on that?
That is a common thought, and in the education world, we call that a misconception. It's a very common thing to think about, and what people think, but it's not correct, unfortunately. So the shadow of the Earth is actually so tiny. So it would never be able to actually cause the phasing of the moon, especially when the moon's not even in line. Good test. Remember, tennis ball being the moon and you are the Earth and have a light source far away to be the sun. Put that light like way at the end of a hallway, like really far, and look at it. And then just where is your shadow, being the Earth, and there's the moon, and you could actually put a piece of paper behind your moon model if the sun's light shining on it, and you would see the shadow of the moon, and that both shadows are pointing in the same direction away from the sun. And so that's a good test to try at home. It's the nighttime side of the moon is the shadow side of the moon itself, because the sun is shining on one side of the moon, and on the other side of the moon, the nighttime side of the moon, of course, is at night, just like we are right now on Earth. We're in the shadow side of the Earth right now because the sun is below the horizon, shining on the other side of the Earth. I hope I haven't made it more confusing, but
one example that I also like to give is like the new moon phase. That's when we are seeing only the shadowed side, and that's when the moon is basically almost in between us and the sun. So if the sun is, say, in front of my face and I'm the Earth, and so my shadow would be going behind me, but the moon is almost in between us, so there's no way my shadow could wrap around.
Correct. And the only time that the shadows actually come in play are on eclipses. So lunar eclipse, the moon does travel through the shadow of the Earth. And that's another good example of the Earth's atmosphere and that gradient of light, because the shadow of the Earth on the moon is very diffuse. But if the moon travels between us and the sun, then we get a solar eclipse, and it is like literally the shadow of the moon is just crossing right over you. And that can only happen about, it depends, up to about 2 times per year for both a lunar and a solar eclipse on average. And you have to be just on the right place on the Earth to see either.
All right, well, thank you very much, Adam. Theo, we have one more question for you. We mentioned how the hotter or colder a star is, that's going to affect its color. If we were in space, would we be able to see that color?
You'd get a little bump maybe from not having a pesky atmosphere winking everything around. Most of the problem is just getting enough light to your eye. You know, our eyes we're used to daytime. That's what we're, kind of optimized to function in. And whenever you go to the dark, you don't see color well unless you have a whole lot of light. So like I said, the example is you can go outside at night and you'll eventually see pretty well, but you'll notice that things aren't colored. They're shades of gray. And so that's our color vision quits working at some point when we don't have enough light. And so that's just a part of our biology. So that's why telescopes help, is to get more light, and that way you can start to see some of the color visually. There are a few stars that are just thinking bright enough that you can notice the color. Betelgeuse is one. Rigel is an extremely blue-white star. So that's a nice contrast since they're right there in the sky close to each other. Aldebaran is I always call it the angry red eye of Taurus the Bull. And the Pleiades are a very lovely blue, especially in the telescope. I mean, they just really stand out. So if you get enough light, you can see the color. But most stars, they're pretty dim, and we just can't do color at that light level.
All right, well, thank you, Theo. Now we're going to head back to Nashville and right here at the Dyer Observatory. And we have Dr. Bob Schweikert with us tonight. So if you've ever been to the Dyer Observatory when we were holding our in-person events, you probably saw this gentleman walking around. He's a fountain of knowledge. He's just a great person to talk to. He's a retired endocrinologist, and he's been volunteering here at the Dyer Observatory for about, actually going on 14 years now. And so tonight, the clouds, I think the clouds have still held off for us. He's going to be looking at Jupiter with our Large Seyfert telescope. So I'll turn it over to you, Dr. Bob.
Well, thank you, Billy. Well, welcome everybody to a nice evening, and it has certainly cleared off from a cloudy afternoon. So what I'd like to do here initially is to share a screen with you that is working right now. As soon as I get it, there we go. This is the Jupiter as we are looking at it right now through the telescope on at Dyer Observatory. And it's a little jumpy and a little bit fuzzy, but the atmosphere tonight is a little bit unstable. With all the clouds blowing out, it's better than it was, but it's a little bit jumpy tonight. And of course, that's why we have the Hubble Space Telescope to give us a much better view without the worry of the moving atmosphere. Jupiter is the fifth planet out, and it is been known since antiquity. It is a huge planet, and it's hard to realize just how large Jupiter really is. But if you were to take the Earth and put it right in here, you would be able to put 11 Earths across the face of Jupiter. So it makes it close to about 88,000 miles in diameter. Jupiter rotates on its axis relatively fast, a little over 9 hours. And as a result, it's a little wider here at the equator than it is from pole to pole. And this is called an oblate spheroid. And it causes some problems for some of the surrounding moons of Jupiter, simply because the gravitational effects are varied as the moons will revolve around Jupiter. Jupiter is the third brightest thing in the sky, the night sky, after the moon and after Venus. And it's reported, which I've never seen it, but it's reported that in some places in the world, that Jupiter can be so bright as to even cast a shadow if you're out at night. So that one, I don't know if that's really true or not. Jupiter is made up of gases, primarily of hydrogen. It's made up of about 10% helium, but helium being 4 times heavier, it actually adds about 25% to the mass of Jupiter. And whether there's a core to Jupiter or not is not fully known. If there's one there, they think it may be about the size of Earth. Others feel that there may not be a core. That's something which is still in the area of theory. The gases themselves are under a tremendous amount of gravitational pull. So as one actually ventures in through the upper layers, the pressure and both the temperature start to increase. And you finally reach a point where it is so much pressure that hydrogen actually turns into what's called metallic hydrogen. And it becomes conductive of electromagnetic energy. And in the process generates a tremendous magnetic field around Jupiter. In fact, the magnetic field is so powerful that it forms bands of high radiation, so that our satellites that go there have to be well shielded. And even Juno, which is in a polar orbit around Jupiter, is far enough away most of the time, but when it comes in, it gets a lot of radiation from these magnetic fields. And as a result, it has a limited lifetime because it gets in very close to Jupiter to make fantastic looking pictures. Now, the bands that you see on Jupiter here, these are very fast moving cloud forms, and they're different colors simply because of the other materials being blown up from lower levels, and they have different types of products in them. There are other gases there. There's ammonia, there's a little bit of water vapor, there's other types of elements that are in there. So as they blow up, then they will cause different colors. One thing it's not showing tonight, of course, is the Great Red Spot. And this is a massive storm. And what I'm going to do, I'm going to drop this off. And well, if I get the button, there we go. And just a second here, I will bring up, if I can, Jupiter. Here we go. All right, here we go. This is a nice picture of it. Actually, you can see how wide it is here, the oblate spheroid of Jupiter in this picture. But it has a Great Red Spot. This is a storm, a giant hurricane that has been going on for hundreds of years. It was not
I don't think we can see your screen.
Beg your pardon?
I don't think you shared the screen.
Oh, did I not? Oh, excuse me. Hold on. I will, you're right. I'll try again. Now is it working?
We can see the live view of Jupiter.
Oh, that is a live one. Excuse me. I'll get my act together here shortly. I got too many buttons to push. Let's see. Share. About there. Now, is it working now?
No, can't quite see it yet.
There? Okay. I will talk about it then. The major problem here is that I'm just not being able to pull up the proper picture. The storm has been on Jupiter. It's been there probably at least close to 400 years. It was not seen by Galileo when he did his first viewing back in 1610, but it was detected by one person probably a few years later. But certainly at the time of Cassini in the mid-1600s, there was a lot of information then about the Great Red Spot. You can probably put about 1 to 1.5 Earths inside of the Great Red Spot. It's just a giant storm, and it's been a permanent picture for quite some time. The major problem with the Great Red Spot now is it appears to be diminishing in size rather slowly. And it really isn't red as you think something being bright red. It's more of a kind of a brownish red in color. Now, Jupiter is quite massive, as I've mentioned, and it's so massive, if you take all of the rest of the planets in the solar system and throw in the asteroid belt, if you want to, Jupiter would still be 2.5 times more massive than all the rest of the solar system, the planets put together. And as a result, it has been a kind of a gorilla, if you want to use that term, for the solar system, in that its gravity has really changed a lot of the solar system over a period of hundreds of millions of years. There's evidence to suggest that Jupiter may have formed where it was and then migrated in and kind of stirred up everything in the inner solar system and then gradually migrated back out to its current position. Now, Jupiter does revolve around the sun in about 11.7 years of Earth years. It also has quite a few of the, let me get rid of this, also has quite a few of the moons around it, 79 at the last count. But the most important ones are the Galilean moons that were discovered by Galileo in early 1610. There was also another astronomer at that particular time who was Simon Marius, who published that he actually discovered the moons prior to Galileo. He published when he published his information, he said he discovered them late December of 1609. Galileo discovered them in the first week of January of 1610. The problem turned out to be that Marius was using the old Julian calendar, and Galileo was a little bit smarter and used the Gregorian calendar, and it turned out that Galileo won the bet. So he was the founder of the 4 moons, and they're named for Galileo as the Galilean moons. The thing about these moons, since we're talking about moons tonight, are really quite unique. And when I had the picture up, let me go ahead and share the live shot again. There we go. If you notice right out here at the edge, there's a little dot right there, and that is the moon Ganymede. And then earlier in the evening, it was about here, and just in the time when we started here around 7:30 to now, it has moved that far. The other moons are not quite visible because they're a little bit further out from our field of vision. The four main moons, when Galileo found them, were orbiting Jupiter. And as a result, he figured that if that was true, then maybe the Earth was revolving around the sun, as Copernicus had shown. And of course, he got into a tremendous amount of trouble with the church at that time. I'd like to spend just a few minutes talking about some of the moons of Jupiter, since we're talking about moons tonight. And the first one around is let me go ahead and drop that down. I'm going to take that off. Is Io, and I wish I could bring up the other screen here if I can. There we go. I hope that's working. Is it working? I'll ask. If it is working, go ahead.
Can you exit out of that?
Yeah. It was down here.
Bring it up real quick. Yeah, just go ahead and click on that. And then go back over here.
Go here.
Share screen.
Oh, and then.
Yeah, for some reason.
Oh, I want this. Will that work?
No, it's not doing it either.
It won't
You
work
know
yet.
what? Let me pull it up on my screen.
Okay, all right. We'll get this worked out. Anyway, did I lose everything?
There's your desktop, Dr. Bob.
Oh, I did. Oh. I'm stuck. Like, you can hear me okay, Nathan?
We hear you.
I'll go ahead and talk. Io is the closest moon, large moon, to Jupiter. It's slightly smaller than our moon. And Io was felt to be a dead rock there. And it was during the passage of Voyager 1, and I believe it was March of 1979, pictures were made of Io as it went by. And I wish I had able to bring up the other slide tonight. I have one that shows a volcano on Io spewing the material, actually a couple of 100 kilometers into space. And it's been found out that Io has about a huge number, here we go, a huge number of volcanoes measuring about 400. In fact, it's the most volcanic object in the solar system. And the question is why is it so doggone hot that it has all the volcanoes? Well, it is very close to to Jupiter. It has an elliptical orbit, so it's passing as it's going around in 1.7 days to revolve around Jupiter. It's going through varying gravitational fields. And also we have the, I don't know where he came from. We also have Europa and Ganymede, who are close by, and they're in orbit in such a way that they're in resonance. As a result, there's a lot more gravitational effect from them also on Io. So Io is like a piece of putty, and it's being constantly molded by passing through the various gravitational fields, and that friction makes it hot. On Earth, we have our tides of water from the moon, and some also from some effect from the sun, and then maybe 10, 15 feet at most, maybe some places in the world, maybe as much as 40, a little over 40 feet. On Io, there's no water, but the land at the equator can go up and down in tidal movements as much as 300 feet. And that friction keeps it nice and hot. The other moon I want to mention very quickly, which is of great interest to everybody, the scientists here, is Europa. And Europa is the smallest of the 4 Galilean moons. And it is composed largely of water. It may have a small core to it, and the top 10 to maybe 30 kilometers is frozen. And their cracks sometimes will form, and actually water can be seen spewing out into space, and that's been photographed. Underneath is felt to have a liquid ocean, and it's also warm because of the tidal effects of going around through the various gravitational fields so that it is warm inside. So there's some conjecture whether there's any life form there, especially if it has a rocky core. You think about the hydrothermal vents on Earth where you have the tube worms and everything else there, that there may be something there also. They've been thinking about going there and drilling a hole, which would probably be many, many kilometers deep to get to the water. But since cracks form and it spews out the material into space, the salt water, then if they can sample that, they may be able to answer quite a few questions. The last moon I want to talk about is Ganymede. It's the largest moon in the solar system. It's actually larger than the planet Mercury. It has a somewhat of a solid surface, but it also may well have a huge ocean inside of it. And also it's warm enough that it's probably a liquid ocean. Back to Europa, it probably has, thinking about it, probably has about 2 to 2.5 times the amount of water in it than we have on Earth. And Ganymede may well have even more. I think we'll go ahead and stop there, if that's okay. And I apologize for the breakdown in the pictures I want to show. But I think I find Jupiter quite interesting, and especially these moons that each one is different and holds a lot of things for the future as far as exploration. Thank you.
All righty, Dr. Bob, let's take just a couple questions, and we've got some others on here, and we've reserved some time at the end, and we'll come back and get to some of those questions as well. Jupiter's day, is it 9 hours or is it?
It's a little over 9 hours, about 9.5, something like that.
Okay.
Right.
And then, just for the sake of time, what would happen if somebody went inside the Great Red Spot?
It would be a giant storm, and they would be blown around at very high speed, and it would be like flying through a hurricane on Earth, only magnified by a magnitude as far as the speed of the winds and everything.
Okay, well, thank you very much, Dr. Bob. So now we are going to go back up just north of Nashville to Theo Wellington again, and she's got a different type of object that we're going to be checking out.
Yeah. Hi. I also wanted to come back a little bit to that one question, because if I had thought about it for 2 seconds, I would have known the answer. If two things take about 100,000 years to go around each other, that's like the orbit of a comet in the Oort cloud. So that's the kind of separation you'd be talking about roughly between, say, the one part of Albireo and the other thing, if they're actually connected. It would be something like that, something on the order of where our comets come from. Way out. All right, let's go back and do a screen share again, and let's see if I can tell which one is the correct screen. No, that's not it. This one. Okay, screen 2. Here we go. All right, so today we're going to go out kind of in the same place we were before, before last time, which is our friend Cassiopeia. It's the big W here in the sky, or the number 3 if you don't like letters, but it's supposed to be a queen sitting in her chair, but I've never seen it like that. And I'm going to see if I can get a little bit of audience participation here, because we're going to be looking at another open cluster of stars. It's kind of cute. It's just actually not that hard to find, which is good, because the telescope I'm using tonight, I'm trying to go really low tech. So this is the telescope I would normally bring to a star party, and it's just a manual scope. So I have to be able to find things actually with just pointing at it in the sky. So where I'm looking here is just off to the side of the last kink here in the W. And there are lots of actually cool things to look at, because the Milky Way runs through Cassiopeia. But if you look there, and you can actually see, I think, some of the brighter stars in this with just a pair of binoculars, but it only takes a really small telescope to see what we're going to look at. So again, this is for scale, what the camera would see. You know, we could fit the whole moon in the field of view. But what we're looking at is right here. So we've got some bright stars here and a whole pile in this little cluster. And although the stars do have some color to them, and if you took a long timed exposure, you'd see some of that, to your eye through the telescope, they're just white. So looking at that central grouping there, I wondered if anybody had any ideas about how you would connect the dots to make a picture. And I will say that these two bright stars, by the way, are not actually part of the cluster. They're foreground stars that just happen to lie in front of the cluster. But they lend themselves so well to the various pictures you can make that it's kind of fun. So last time I was showing Carolyn's Rose Cluster, first described by Carolyn Herschel. This particular group instead was cataloged by her brother William. So do we have any active imaginations out there? I am not an artist, okay, but one of the names that has been associated with this cluster is the Dragonfly Cluster. So here's my really unartistic attempt to see that. There is another name, and this one I do see, and that's not a bat. It's supposed to be an owl, right? You got the glowy eyes, the wide wings, and that's kind of cool too. But the one that just really hit me when somebody said this is what it is the ET cluster. Because you can totally see ET, his two glowy eyes, and I think it's totally appropriate. I have been told that small children now, right, they've grown up. It's been a couple of years since that movie, and actually a lot of kids don't know who ET is. This is incredibly sad. Somebody needs to tell them. But in any case, for me, that works astonishingly well, that this is the ET cluster. Its actual name is, that's the NGC 457. And yeah, you could put an extra star in there as well if you want to really make it ET. But that's otherwise what we're looking at. And this is only a 7-second exposure with the camera that I'm using. So it's not much different. Again, it picks up a few more stars, and all that little faint speckling there, all that is noise. The cameras have some noise, and this one's not taking it out right now. But I think that's a good, clean fun. And I just think open clusters are really cool. This one, again, is several hundred light years off. It's actually really young. It's only about 21 million years old, which is practically nothing. Let's see. So that's a deep exposure. If I were to take a camera and soak it for an hour, then you get more stars. And a lot of that actually isn't noise at that point. It's just stars because the Milky Way, again, is there and it's full of stars. So, but 21 million years is hardly anything. I'm not sure when our solar system formed that the Earth would have been solid at that point. So those are very young stars. Again, still kind of tightly clustered together because they were made out of the same cloud of gas and dust, which has since blown away. But very pretty little grouping. And hopefully some of you had imaginations and can see some other things. You know, there are never right ways and wrong ways to see some of these. Every now and then I had teachers want to know what is the correct answer, and there isn't one. You know, people have been playing connect the dots for centuries with just the stars we see with our eyes, and every culture around the world had their own way of connecting those dots. So the noise here is all this little faint junk. That's camera noise. These the camera that I'm using, it's really fun for planets because it can take fast video. But if you're trying long exposures, it has way too much thermal noise. And actually, this thing over here is a bit of an artifact because I'm trying not to show that you can actually see the amp on the amplifier on the camera sometimes. But it's a nice, easy way to show this about what you would see if we were, instead of online, we were actually at a star party and you were looking at that cluster with me. All right, so it's kind of a bonus because, again, I really want you guys out there to go out and look at the sky. So again, if you look up at the summer triangle, we've got, there's Deneb, right? Here is Albireo we were looking at earlier right here. So this time we're going to look at this line between Altair down here and Vega. And maybe about a third of the way along that line, there's this, again, cool little group of stars. Now, this isn't anything special. This is actually just a chance arrangement of stars. But the human eye likes to make patterns. Even if there aren't any there, we will make them out of things, right? We see faces in donuts and things like that. So this is the same sort of thing. So about 2 binocular views, that won't work, will it? Half of this is about what a binocular view would be. If you move about 2 fields in your binoculars up, you're going to run across this ridiculous little asterism here. That's what we call a pattern of stars that we kind of all recognize. And I think this one really earns its name. This is called the coat hanger. So no mythological creature, is just a plain ordinary object, but boy, it really stands out. So that's a little bit of fun and something that anybody with a pair of binoculars can find up there in the current night sky. All right. Upside down flower, that could work too. Oh, which direction is this? The summer triangle is almost directly overhead. Let's see if I scrolled back. Oh, let's see, up. I know one of the early slides, and I'm going to be bouncing back here to the other one. Cassiopeia is north, right? It's rising in the east right now, so this is very much looking to the north-northeast. So there's our friend the moon. Let's get out to the far view. So the ET cluster, here's the North Star Polaris. There's the Little Dipper, which we can't see in Nashville except for these 2 stars right here in Polaris. There's the Big Dipper swinging low. And then Cassiopeia is rising up. So that's where that group is. And then the Albireo is almost straight overhead. It's actually difficult to get to with the telescope at this time of night because it is straight up overhead. But if you start at the moon and you head upward past the planets tonight, you would see the triangle straight overhead. All right. Yeah, in a fast exposure, but you know, I wanted to see the stars too, so your eyeballs don't have so much thermal noise. It's kind of nice. Or we have really good software that takes it out, one. And if you're wondering what this thing is over here, this is also something you can find with binoculars. That is the Andromeda Galaxy. And we'll probably have that. I'm hoping to talk my better half into bringing out a large telescope next month. And maybe we can have a little bit of fun with that, because that's our largest, well, it's our closest galaxy neighbor in space, if you don't count our little satellite galaxies. And it's a great big beautiful spiral. But if you head that direction, if you take these stars in Cassiopeia here at the end of the W and just start tooling in this direction, you will run across it. It looks like a piece of cotton candy stuffed up there in the night sky. So you don't need an expensive telescope, I think is what I wanted to say tonight. You can actually have a lot of fun with small equipment. And in fact, if I stop sharing here, just get back to me or Nathan. It only takes a modest telescope to actually have a lot of fun. It's fun to have the cool toys too, but it's actually easy to have a lot of fun with very inexpensive. And by that, I mean the telescope back here I bought 15 years ago for $300. So that's not bad. All right.
All right, thank you so much, Theo. That was really cool. I had never seen the ET cluster actually drawn out, so I never got it until you actually showed it to us.
It's my new favorite friend. It really is. I love it.
Yeah, so I mean, now every time I look at it, that's all I'm going to be able to see. But yeah, talking about how we can find patterns in things, the M11 cluster is called the Wild Duck Cluster. And apparently some people see like a V of stars that forms like a flying, like a, you know,
yeah,
geese or ducks flying in a V formation. But I guess I could see that, but yeah, I guess if I was
I have never seen that myself. I've looked at it, I've taken a picture of it, and I don't see ducks, but okay. You know, it's everybody's different. And that is not a feature, by the way, this little green dot here. That is just my camera is picking up the light of, you know, the camera light that says I'm on is bleeding through to my PC camera. Oh, well.
Okay, well, thank you again, Theo. All right, and so now we're going to go out to West Tennessee over to Jeremy Beldman, who is with the Memphis Astronomical Society, and he's going to be talking to us and showing us some other deep sky objects. So Jeremy, take it away.
Thanks, Billy. I'm going to go off script here for 1 minute. Adam, it looks like you may have Mars. Do you want to go ahead? Okay.
No.
Okay. How's my audio? Give me the thumbs up. Very good. Well, thank you. Tonight is not necessarily the best night to show the two objects that I'm going to show you, not only because of the massively overcast skies that we have here, but even if it was clear, we have a bright moon, a bright gibbous moon. So the two objects I'm going to show you are what are called deep sky objects, and they're part of the Messier catalog. They're nebulae. But they're worth looking at. I mean, they're typically best in the month of August, but even into September, they're great targets into late September if you can catch them in the early sky. So I'm going to go ahead and share my screen here in just a second. But first of all, like the Barnard Astronomical, we're the Memphis Astronomical Society. We're a group of amateur astronomers in Memphis, and we meet once a month. And we have regular astronomy presentations, and then we also have a couple of dark sky observing sessions if it's clear, as well as public observing sessions. For instance, tonight is typically our International Observe the Moon night, where we would meet in town to show people the moon. Of course, we're shut down because of COVID, and also we have cloudy skies, but that's basically what we do. Our meetings are free and open to the general public. It's really for anyone who has a passion and an interest in astronomy. So let me go ahead and share my screen here. And I'm going to bring my presentation up. So hopefully everybody can see that all right. So we meet at a place called Burton Sugar Farm a couple of times a month if the weather's clear. And here you can see a picture of Keith and myself. Keith is one of my buddies. He's an astrophotographer. And you can see us here underneath the dark sky, the Milky Way. When you don't have a moon and you're in a dark sky location, this is essentially what you would see, just a swath of stars that makes up the Milky Way galaxy. So it's really cool. If you ever have an opportunity to get out to a dark sky site and see these targets, it's really amazing. So kind of a quick rehash here. And I showed some of this video footage last month, but my other buddy, Brian, owns what's called a night vision eyepiece. Now the telescope here on my left is my telescope. That's a 10-inch Dobsonian. It's one of several telescopes that I own actually. And this is actually a good beginner telescope. We got this question earlier tonight. What's a good starter scope? I always recommend either a 6 or an 8-inch Dobsonian. In this particular case, it's a 10-inch. It's very portable. You can transport it to a dark sky site like we're here. Also, it fits in the back of it could fit in your trunk, or, I have a small SUV. So it's very easy to transport, and you can set it up really quickly also, only a couple of minutes to get it set up. Now, this device right here on the side is called a Telrad. It really is an essential piece of equipment for finding things. If you have a Telrad on your telescope, you should be able to find, not only the bright stuff like the moon and the planets, but even some of the deep sky objects pretty quickly. With this setup, I can usually get set up in about 5 or 10 minutes, and I could find the two objects I'm going to show you tonight in about 30 seconds. So it's quick and dirty, and I like that for backyard astronomy, because if you're just testing out the hobby, it's a good way to get your feet wet to see if it's really for you. Now, Brian owns a night vision eyepiece similar to what you see, with military personnel. And they're not cheap. You could probably buy 15 of these telescopes for the cost of one of those eyepieces, just to give you an idea. But it really gives you a good idea of what some of these objects look like in the eyepiece of a telescope. So here again, we took an iPhone, just a regular iPhone, put it on an iPhone holder, connected it to the night vision eyepiece, and then put it into the focuser of the 10-inch Dobsonian telescope, turn it on, and then just kind of look for something in the sky. And then it actually appears as either a picture or a video in the iPhone. In this particular case, this is a nebula, the Lagoon Nebula, which I'll show you in a second. So the two objects I'm going to focus on tonight are M8, the Lagoon Nebula, Messier 8, and then M20, the Trifid Nebula. And they're both located in the constellation Sagittarius. Now, Sagittarius is a centaur, but most of us recognize it as the familiar teapot. Very easy to find in the southwest sky in the summers, and then also in the early autumn. Just look for the teapot, and it's very rich as far as targets are concerned. And here you can actually see a professional image of what this constellation looked like and what's around it. And you can see you're looking right into the disk of our galaxy toward the nucleus. And there is just a massive amount of stars because you're looking right toward the center of our galaxy. In fact, if you get to a dark sky location, it'll literally look like a cloud of stars right near the asterism of the Sagittarius teapot. There's so many stars between us and the center of our galaxy that theoretically you should be able to stand outside on a dark night and read a book just by the starlight. The reason why it's dark at night is because there's so much dust between us and the center of our galaxy that it blocks out most of the starlight. The exception being Bada's window, which is kind of an area with dust and kind of gives you a little window where we can see stars that are closer to the nucleus of our galaxy. But here you can see, it's just rich in this chart here from free charts of Messier objects, most of them globular clusters. I mean, you can actually match them up here. M7 is Ptolemy's cluster. You can actually see it right here in the image. And then several other ones. The two we're going to look at tonight are M8, and the Lagoon Nebula, and M20, the Trifid. And you can actually see them right here. This is M8, and then this is M20. And again, they're located right here on the ecliptic plane, which is the plane that our solar system and planets travel on. Now, this image gives you a little bit better idea of where they're located in the disk of our galaxy. See, here's the nucleus of our galaxy. Now, the sun, where we are, is located right about here, about 25,000 light years from the center of our galaxy, about 8 kiloparsecs away. Lagoon Nebula would be located right about here, and then Trifid here. Now, this is an older picture. We have a more updated map of our Milky Way galaxy, but it really gives you an idea that we're riding on a disk of stars, and there are these spiral arms where all the action is. There's a density that propagates through the disk of stars, causes gas clouds to clump and condense and ultimately form new stars, star clusters that eventually birth stars like our sun. And that's what these two objects are. They are literally stellar nurseries where new stars are forming. Here's an image of the Lagoon Nebula M8, and it's just a brilliant image. It's not one of our astrophotographers. You can find this in Wiki Commons, but it gives you an idea of what a professional or an astrophotographer would take if they were looking at M8, the Lagoon Nebula. Now, in the eyepiece of a telescope, here's what it looks like. Now, you can see here, it's just a gray fuzzy patch in the upper of the screen. And of course, it's moving because I don't have it on a tracking mount. So the Earth is moving, not the telescope. So every few minutes, I've got to adjust my telescope to get it back in the center of view. And there you can see it in the center there. It's a gray fuzzy patch. You don't see color like you would in an image. And here is actually an image that Keith Latulay, my buddy, and fellow astrophotographer took of the Lagoon Nebula. But you don't see that in the eyepiece of a telescope like a 10-inch Dobsonian, because light coming into the telescope to stimulate the rods and the cones in your eye. So all you see is basically a gray fuzzy patch. But I tell you, when you see it in the eyepiece of a telescope, a good beginner telescope like an 8 or 10-inch Dobsonian, or even in binoculars, it's really spectacular. It's really cool to bag this image by yourself. Now, again, this is a stellar nursery. This is where new stars are forming. It's a gas cloud of hydrogen. And I'll talk in just a second in more mechanics about what it is. But here you can see it. Again, I'm looking through the eyepiece of a telescope, in this case, a night vision eyepiece connected to an iPhone, 10-inch Dobsonian, very basic beginner scope. That's what the M8 Lagoon Nebula would look like. Now I got to get a little quantum mechanics on you here. Just bear with me, okay? You see the red color of the nebula. That's very characteristic of this nebula. It's what's called an emission nebula. And the gas, in most of the gas in this nebula is hydrogen. And there are nearby stars that are just spewing off massive amounts of radiation that are causing this gas to excite. Now, in quantum mechanics, electrons can only exist in discrete energy levels. When the gas gets excited, the electron jumps from a lower energy level to a higher energy level. And when the gas de-excites, in other words, falls back down, the electron falls from a higher energy level back to the second energy level, it can give off a photon. That's called the Balmer series. Now, in the case of a transition from the third energy level to the second energy level, it gives off a wavelength, a photon that has a wavelength of 626 nanometers, and that's what our eyes translate as red light. We call that hydrogen alpha. And you hear this term very common in astronomy. It's called hydrogen alpha. In fact, astronomers, amateur astronomers, and even astrophotographers, an essential tool in their toolkit is what's called a hydrogen alpha filter. And they use that to filter out the narrow band of light so that they can see nebula in urban areas where there's more light pollution. So that's what we mean by hydrogen alpha, and that's where the red color of the Emission Nebula comes from. This is an emission nebula because it's literally emitting a photon of light when the electrons de-excite from the third energy level to the second energy level in a hydrogen atom. So that's true of the Lagoon, and it's also true in the Trifid Nebula. This is M20, again, a professional image of the Trifid Nebula, one of the most famous images in all of astronomy. And you get 3 for the price of 1 here. On the right is the kind of the reddish pink area. Again, that's an emission nebula like Lagoon, where the ionized hydrogen gas, the electrons are de-exciting and emitting red photons. So they're emitting red light as translated by our eye. So that's what this red area is here. Now, the blue region on the left, that's called a reflection nebula. And that's caused by nearby massive O and B type stars that are reflecting off of the gas around it. So the blue light is reflecting off of the ionized gas, and that's what's causing the blue light. And then, of course, you have these dark here. That's the dark nebula. So this is the pattern I look for in the eyepiece of a telescope when I'm trying to find this object. And here's what it looks like in the eyepiece of a telescope. Again, gray fuzzy patch. And again, it's moving in the lower right in this particular case. And then I got to recenter the telescope again, but there you see it. You just basically see a gray fuzzy patch. This is what it would look like if you had an image of the Trifid. Again, this is from Wiki Commons. So, but you don't see that in the eyepiece of a telescope. Again, similar to Lagoon, all you see is a gray fuzzy patch. And again, I got the eyepiece of my telescope, but here it is. You can see the very distinct gray fuzzy patch that is the Trifid Nebula. And again, it's a stellar nursery similar to Lagoon where new stars are forming, but that's what it looks like through a beginner telescope. You just see a gray fuzzy patch, no light, of course, because there isn't enough light coming in from the telescope to actually see color. So if you had a larger telescope, I think 30 inches is the minimum size you would need to start seeing color. And I'll end with this. This is an image that Brent Ellis, one of our astrophotographers, took. He's located in Olive Branch, not too far from Memphis. You can see both of them here. You can see Lagoon on the left, and then you can see Trifid in the lower right. And you actually get another Messier object over here. This is M21. It's a little star cluster. So really cool image. If you have a wide field, either eyepiece or camera, or it's a great binocular target also, you can get both of them. So anyway, that's about it. Just kind of a quick look here at both of those nebulae. I'll turn it back over to Billy at this time for any questions.
All right, thank you so much, Jeremy. We do have a couple of questions. So first one is, why is it that in certain places in the world it's bright and clear at nighttime, and you can read or see the stars more clearly than in other places? Apart from the air and light pollution, is it also because of, say, dust in the galaxy?
Well, the southern hemisphere, I've heard, is a lot better than the northern hemisphere. If you can get to the Atacama Desert in Chile, that's one of the best spots in the world. I've never been there, but my colleagues have, and I guess it's really incredible. You get a better view of the Milky Way down there. you're in a higher elevation, which means you have more stable atmosphere, better seeing conditions. You're in a drier climate, so there's not as much moisture in the atmosphere. So I'd recommend it, even though I've never been. It's one of my bucket list items, but the southern hemisphere is definitely better than the northern hemisphere for Milky Way stuff.
And so that is basically because of the light pollution.
Exactly.
And there was another question. Do the stars move out of the stellar nursery as they get older, or do they basically stay there?
Yeah, they actually form there. They start off as a cloud of gas, then they form a cluster of stars, and they stay together for a period of time. We see this with open clusters like the Pleiades, and I believe M68 is another good analogy for a cluster like one that our sun would have formed in. Over time, as they travel around the galaxy, gravitational interactions from other stars and other objects in the galaxy will cause the cluster to evaporate. So they stay together for a little while, and then they just sort of go their separate ways over a period of millions of years. And that's kind of how stars like our sun form.
And I'll just add that especially when these big hot stars form, they put out so much light and they have particles streaming off of them called the solar wind. That goes out into that nebula and not only excites it, but it tends to push a lot of that gas away. And so in the wintertime, when we get to look at the Orion Nebula, we'll actually see how the nebula kind of has a bowl shape because of the really bright stars. There's one in particular at the center of that nebula that's really kind of eroding away the nebula. So we think of, like the ET cluster. If we went back about 10, 15 million years, then we might see something like the Lagoon Nebula, right?
Yep, exactly.
Right.
You
Well,
can think of it as the raw material for forming new stars.
Mm-hmm. All right. Well, thank you so much. Well, Adam, how are things looking for you?
I am prepared to talk about Mars for just a few moments, but it is like totally socked in, and unfortunately we got a few moments of like, oh, I could see it in the disk. I saw the polar cap. I saw some of the dark basalt areas, but I'd like to at least talk about it for a few moments.
Okay.
Yeah.
I was going to say we could go ahead and move on to our next presenter, and if it looks like maybe it'll clear out, just come back and try it then.
I don't think so. It's going to be behind a tree.
Okay, I got you.
I'll just be real quick.
Okay, yeah, please.
Okay, thank you. So, unfortunately, Mars is not being visible right now. I'll just talk for a few moments. Maybe it'll pop out later, but I'd like to bring up about the topic of Mars, because what's going to happen very soon, as you can see the date on this image, that Mars is going to be the closest to Earth in its orbit on October 6th. And just think about, it's like looking down on a racetrack, where if you had a series of circular racetracks going out from the center, and an inner circle is Earth, with being the third planet from the sun, and then the next racetrack out is the fourth planet from the sun, and that is Mars. And so the farther a planet is from the sun, the slower it goes in its orbit. And so Earth will overtake Mars in its orbit, but there's a point in which Earth is kind of catching up to Mars, and it's not getting next to Mars. It's just the separation between the two planets is the closest because of the positions of those two planets. Now, there is some variation from 1 year to another. It takes about 2 years for this to occur, where we get close to Mars in our two respective orbits. This is actually one of the better times. And here's a scale model. I hope you can actually see it in this image. So when Mars is the farthest from the Earth, when it's on the other side of the sun in its orbit, way far away, it looks teeny tiny, 3.5 arc seconds in apparent size. And then what's happening on October 6th is 22.6 arc seconds. And you can see it's much larger looking. You can actually see a little bit of surface features there. Now, it's not like it's one day it's really big. This is actually over about a 2-month window when it's nice looking in the sky, when it's larger looking in the sky. And then we hear the common thing about, oh, I heard Mars is going to be as big as the moon. Well, no, there's the moon. All of these images are to scale. So you can see the moon, that I'm actually a little insert inside, but you can see that there's a huge moon compared to how small Mars looks even at its closest. So it's a real challenge. You do need a telescope, you do need magnification. And obviously this is a high res image kind of photograph. It's actually a composite from space imagery, spacecraft imagery, and I've labeled this, but this is what we would have seen tonight. And on the bottom right, you can see a little white area. That's the southern ice cap made of frozen water. The carbon dioxide that was frozen has evaporated because it's summertime in the southern hemisphere on Mars right now. I did see some of the dark areas which are labeled Terra Meridani and Solus Planum. So I did see kind of that darkish region for a moment. This actually I was hoping to see, but we didn't get to see it. Hellas Planitia, which is actually a sandy, much more sandy area. The color of Mars is actually from rust in the soil. We call it soil. It's not like dirt here on the ground, but you know how we have the red clay around here? The reason it's red is the same reason Mars is red: oxidation of iron in the dirt. And so that's why Mars has that red color. And the dark areas are exposed basalt rock. So it's lava rock. And we have that on Earth, we have it on the moon, and also on Mars. So it's a common geologic feature. So I'm actually going to stop there with that because I don't want to take too much time. So I'm going to give it back to Billy, and we'll continue on.
All right, well, thank you, Adam. I don't see any Mars questions yet, but I was hoping that you could comment on something right quick about global dust storms on Mars.
Yes.
I was going to share a screen, if you wouldn't mind kind of talking a little bit about the image.
Sure. Go ahead.
There you go.
Okay, if I talk, will they still see this image? It looks like it will.
Still hear you.
Okay. All right. Here's the bane of the astronomer. So what will happen is every once in a while, a dust storm will form on the planet Mars. Now, we see two different images here. The one on the left, June 26th of 2001, and then September 4th of 2001. Very different looking. And what's happened is that, yes, Mars is essentially like a desert world. There's sand everywhere. It is very fine particulate type of sand. It's like a dust, okay? And one of the bad things about it is that dust also has a lot of jaggy material in it. It's very coarse, and this stuff is nasty. But it also gets elevated into the thin atmosphere of Mars very easily. So there are times in which a dust storm will form, like you would see in a movie of a desert here on Earth, but it would just kind of continue and get bigger and bigger until that dust and sand covered the entire planet. And so that's what you're seeing on the right image. You can kind of see some dark area there, which is actually the same surface feature. Yes, he's pointing it out. But it's like, this obscuration of the entire planet. And so that can occur. Also, what's pretty cool to see on Mars are dust devils. So they kind of look like little tornadoes, but they're very mild, and in fact, they've been help because you would get a temperature difference on the surface of Mars. And so with the temperature gradient, that's what it's called, the temperature difference, you would end up with swirling air mass, and you would get what's called a dust devil. They're about 30, 40 feet tall, maybe 5 feet wide. They can't hurt you if you were there. But a dust devil once actually went over the solar panels of there's a dust devil, thank you, Billy, that went over a solar panel of Curiosity. I can't remember which one, but one of the spacecraft rovers on the planet Mars. Maybe Spirit. You're muted.
It was either Spirit or Opportunity. Yeah. And the cameras on there even captured dust devils going by.
Yeah.
It was actually Opportunity.
Was it up? Okay, thank you. There are so many rovers on the planet now, it's hard to keep track. But it was neat because it actually just went right over the solar panels now, and it cleaned off those panels. And all of a sudden, the energy boost, brought that craft back to life, so to speak, because the dust was covering those panels. And I'm thinking, why don't they just have like a windshield wiper? just knock the dust off every day. So sometimes the simplest solutions work the best. Coming up, and I'm terrible with remembering all the spacecraft names, but there's a craft that's going to Mars, and it's going to have an actual drone on the craft. So after it lands, this drone is going to have essentially a GoPro camera and fly around above the surface of Mars as one of the exploring devices. And I was actually lucky enough to be able to talk to one of the scientists who was talking about the prospect of that project years ago. This was a long time ago. And I brought up about the camera, and they said, we've already got the camera. And it's actually, they were going to use a GoPro. They said right off the shelf, it was actually space ready. So, yeah, I know it's kind of neat to think about that, but a couple $100 camera, they just slap it on there onto a multi-million-dollar spacecraft. So that's going to be landing. They're actually going to be using this opposition as an opportunity for launch and landing. So it's going to be happening in the next few months. So I'll stop talking because I know others have great stuff.
All right, well, thank you, Adam. I think that was Perseverance is the new rover, but don't quote me on that. I just wanted to end this segment by just saying that this was a view taken from the Mars Reconnaissance Orbiter. So it's up in space or around Mars orbiting, taking high resolution videos, and it's caught a number of these dust devils. And so this dark line here, it's not actually like darker rock, that's actually the shadow. So they, based on knowing where the sun is and how long the shadow appears to be, they can actually determine that these dust devils, they go up quite a bit higher than what, say, an Earth dust devil would be. So,
okay.
All right, well, thank you very much, Adam. And let's see, now we are going to take a detour and go all the way up north and visit with Sabrina Berger, who is a graduate student at the McGill Space Institute in Montreal, Canada. So she got her bachelor's while she was here in the United States out in California. And so now, as she likes to put it, she spends half of her time in freezing weather there. So up in Canada, that is. So tonight she's going to talk to us about exoplanets. All right.
Great. Can you see my screen, Billy?
I can.
Awesome. Okay. So as Billy said, I am a graduate student at the McGill Space Institute in Montreal, Canada. And this is a video of the Northern Lights taken from a little bit north of Montreal. And it was taken by an amateur astronomer. But tonight, of course, we're doing all of our observing from Tennessee. So this is just another picture of Mars, or actually a video of Mars taken with Dyer Observatory, September 10th, 2020. You can actually see some of the distinct features of Mars, just kind of to re-show an actual live image of Mars that we can see from Earth. And then we also saw tonight Jupiter, and here's another video taken from Dyer on August 25th of this year. And you can see Jupiter's red spot, which was discussed earlier, which has this crazy storm activity going on. And I'm not sure if it was mentioned before, but the size of that red spot is actually, we could fit 2 Earth-size planets, lay them across the spot. It's that large. So in this talk, I'll not only be talking about planets in our solar system, but also planets that we can find outside our solar system in our own galaxy. So to start off, astronomers like to characterize planets into being gas giants or rocky planets. And of course, the best way to think about that is starting with planets that we know best in our own solar system. So on the left, this is Jupiter, taken with the Hubble Space Telescope, a really powerful telescope that was launched into space and took great images for us. And so gas giants are mostly made of hydrogen, helium, and you can kind of think of them as being like big atmospheres. And they have a very small core compared to rocky planets, which on the right, so this is just one example of a rocky planet in our solar system. Other examples are Earth and Venus. So this was taken with the Rosetta spacecraft, which was actually going to observe a comet, but kind of did a flyby observation of Mars. And then this was just talked about, but this is kind of in the stormy season of Mars. As you can see, these white areas on the bottom and top of the image. So rocky planets are way more rocky. So they contain a lot more minerals, harder minerals that we know on Earth. Kind of a lot of material similar to quartz. If you've ever gone to your local rock shop and picked up like a quartz piece of rock, and usually have, or well, at least for the rocky planets we know so far, we believe they all have iron cores that are much larger than gas giants. But this slide is very not to scale. We can actually fit 11 Mars-sized planets inside Jupiter, and we could fit 2 Mars-sized planets inside our own Earth. So gas giants tend to be much larger than their rocky planet counterparts. So you might wonder, we know all about the star, our own host star, the sun, and we know we know about the planets in our solar system, but what about all the other stars that you see when you look up in the night sky? Are there any planets around those stars? And the answer is a very strong yes. So this is a video of from the first exoplanet detection to the detections today. I'll play it a little bit quicker. It's kind of slow. There you go. Oops. Sorry about that. So you can see that initially when exoplanets were discovered in the early 90s, there wasn't many exoplanet discoveries until actually about 2010. So each of these circles popping up is a exoplanet system that has been discovered around some star that was observed. And if you look, actually the most common color here is kind of this purplish blue, which were planets discovered with the transit method. So each of the different colors was a different way of discovering an exoplanet. And that is the most common way to discover an exoplanet. So it's actually not too difficult to understand the way astronomers detect these exoplanets through transits. So this is a little GIF kind of showing a planet, so this black circle rotating around a star. And so as the planet goes around the star, it blocks out a little piece of the light from the host star. And when we see that dip in the brightness of the star, we infer that there's a detection or there's a planet surrounding that host star and orbiting it. So it's kind of like if you maybe put your hand up to a ceiling light and block the light a little bit, you'd see a dip in the brightness in the light. So there's a big mission done by NASA called Kepler that discovered about more than half of the exoplanets that have been discovered today, 2,600 planets using this method. And there's been over 4,000 exoplanets discovered using all of the different methods. using both space-based and ground-based observatories on Earth. So this Kepler telescope that I was talking about, a great exoplanet astronomer at the University of Chicago named Dan Faberke put together this video showing multiplanetary systems. And so these are all discovered with Kepler. And the redder the color means it's a larger planet, and then the greener or yellowish planets are smaller. So these are all multiplanetary systems discovered with Kepler. And I think whenever we talk about exoplanets, the question of whether or not planets can be habitable, or there are planets outside of our solar system that are habitable, comes up. And it has a lot to do, astronomers talk about the habitability of exoplanets depending on their temperature of the planet. And that can be how close it is to its host star. So for the Earth, we're in this kind of Goldilocks zone where we can have liquid water on our Earth. It's not too cold, too hot. Humans can kind of live at a comfortable temperature. So there's been many potentially habitable exoplanets. So planets falling kind of in this Goldilocks zone around their host star, so being the perfect distance from their host star, and some artist depictions of potentially habitable planets ordered in distance from the Earth, which is in light years. So it takes so the time it takes light to travel 1 year. So going all the way up to 1200 light years, that means that it took 1200 Earth years for the light from that planet to arrive at our telescope and detect that planet. And then just showing on the right side, Jupiter, Neptune, Earth, and Mars to scale for these other exoplanets. So these are all rocky planets, like we just learned, and they're much, much larger than Jupiter. Oh, and the planets are much, much smaller than Jupiter. Jupiter is much, much larger. Sorry about that. So I think before ending this talk, I wanted to take a look at a planet that's much closer to home, namely Venus, which is the second planet from the sun. And it actually has the longest day out of any of the planets in the solar system. Its day is about 244 Earth days. And it actually takes longer for Venus to rotate than it does for it to rotate around the sun. And it's interesting, Venus is actually hotter than Mercury, which is the closest planet to the sun, despite being further away. And this has to do with the thick atmosphere on Venus, which is full of carbon dioxide and traps the heat inside the planet and kind of causes a greenhouse effect to occur, like we also see on Earth. So this is an old picture of Venus, actually, from 1974, from the NASA Mariner spacecraft. And as you can see, Venus has this really thick atmosphere. And you might have heard in the news recently that there are some claims from scientists, very reputable astronomers, that maybe there could be life on Venus. And to understand kind of this detection of potential life on Venus, we have to first step back and see kind of how astronomers tell what kind of stuff is in a planetary atmosphere. So if you shine a light through a prism, so you can think of these white triangles here as prisms, maybe you've done this in your science class growing up or something like that, you can see that there's a continuous spectrum. So you see all the frequencies of light. But when we place a material in between the light, some of the frequencies of light actually get absorbed by specific materials. And when we break the frequencies of light up again, we can see these missing frequencies from the elements that were absorbed, that absorbed the light. So we, as scientists, we've studied very well specific frequencies that have that correspond to different elements within materials that when light passes through them, we don't see. So that's exactly what astronomers did when they looked at Venus's atmosphere. They detected phosphine, actually a very smelly gas. It smells like garlic, I've heard. I've never smelled it myself. And it's super toxic to humans. And it's actually used in fumigation to get rid of pests. So it's kind of, initially you might think, wait, how could phosphine indicate that there's any potential life on Venus? So there's actually no currently known physical pathway for phosphine to be created in Venus and in its atmosphere. And we've seen phosphine on Earth coming from biological processes. So phosphine is called like a biomarker, which means it could be produced by microorganisms in their kind of biological pathway. And it's kind of suggested that potentially these habitats for these biological things, microorganisms, whatever they may be, could be actually in cloud decks, in the cloud decks of Venus. So in the future, many astronomers will be looking more towards Venus to confirm or deny the presence of life on Venus, but still very promising and exciting results. So thank you very much. And if there are any questions, I'll take them now.
All right, well, thank you very much, Sabrina. I'm waiting to see if we've got any questions coming in. And while we wait for just a moment, Adam, do you want to share your screen right quick just to show Mars or?
Sorry. Yeah, hang on one sec. You should be seeing it.
Wow.
See that? The exposure, it's going in between, you know, faint and bright. So
Oh, okay.
Testing, but hang on one sec.
Well, I can see the polar cap down at about the 5 o'clock position.
Yeah. I have to be real still. So you see the polar cap. Let me go just adjust the exposure just a touch. Hang on. There. Yeah, we're getting in between. Whoa.
Oh, yeah. Yeah, there we can really see the polar cap at the bottom, right?
See the polar cap, and you see that basalt area. That can you see that kind of darker area in the middle?
A little bit, yeah.
It's a little hard, I know, but it is there. It's more apparent on. I'm seeing actually a number of features more detailed on my camera, but by the time it goes through zoom and everything, it's kind of washed out.
Right. Okay.
Let me. 1 second here. I could probably. Whoop. Well, I don't know. I think this is going to make it too difficult for me to try to share your. But anyway, we're able to at least see. Mars.
Right, and we can definitely see that prominent little bitty polar cap at the bottom right.
Yes, that's the southern polar cap, and you see the dark area. There's, you know, I'm looking at a little image, but you can see a darker area in the middle, and that's that basalt rock. But hey, it's better than nothing.
All righty. I don't think we have any questions for Sabrina yet. So I'm going to go ahead and go to my quick presentation. So to do that, I'm going to have to turn off the light. Well, actually, before I do that, let me show one other thing here. All right, let's see. Adam, can you stop or are we seeing your screen still? Maybe not. Oh, it's just your, sorry, it's just the way you're projecting. Okay, so can everybody see me all right?
Yeah, we got you, Billy.
Thank you. All right, I'm really overexposed, at least part of me here, but I'm gonna kind of duck out of the way here. So what I'm using tonight is a 16-inch astrograph. So it's a really wide field telescope, and this is actually on loan to us from former VU Board of Trust member Mark Dalton. So we thank him for his opportunity to use this. But I was going to do a little bit of deep sky imaging, and of course, I said that a little bit too loud because I can actually see the clouds coming up, but I do have some pictures I've taken beforehand. So anyway, I'm going to switch over to a a live view here from the telescope. Give me 1 second. And all right, so now we should be able to see something. So right now it just looks like a cluster of stars, and hopefully everybody kind of see that. Doesn't look too terribly interesting. This is actually the M16 cluster. This is another one of these open clusters, similar to the type of cluster that formed the ET cluster. And this is actually a 1 second exposure with a cooled CCD camera. But I just want to kind of give you an idea of what it might look like, especially in moonlit skies, to just your eye if you were looking through a telescope. So it doesn't appear to be that much there. But what I'm going to do, I'm going to bring up the exposure now to about 30 seconds. And while that does that, I'll tell you just a little bit more about this. So this is so if you actually find this in the sky, it lies in the band of the Milky Way. Our galaxy is a big disk of stars and gas and dust. So a lot of the material to make these stars is within the disk of the galaxy. And so especially in light polluted areas, you won't see a lot of the subtle features. And so this is what this cluster will look like to your eye. But if the clouds haven't gotten in the way yet, here's what a telescopic view will see. Let me reset the view just a bit here, and it may be too clouded out now. Let me see what we got here. Yeah, it's a little bit too clouded out. Well, luckily I planned ahead. Let me pull up one of my other images here that I took literally just about 10 minutes ago. It's like perfect timing. Let me find it here. Yeah, here it is. So here's this same view. Let me share, and here we are. So this is a 60-second view. So now it looks noticeably different. You can still see those same bright stars we were seeing before. You can see a lot more stars. This view was actually taken when we had some very thin clouds passing through. So the nebula that we're actually seeing here is what we call the Eagle Nebula. But now we can start to see some of the finer structure that if you're in a really dark location, under very, very dark skies, no moon out, no light pollution, and you've got a big telescope, you can start to see a little bit of this nebula here. But kind of going back to what Jeremy was showing us with M8 and M20, this is a very similar type of object. So this is a large cloud of hydrogen gas that has formed stars. It's about 7,000 light years away, but relatively speaking, it's in kind of our local galactic neighborhood. I mean, in our little section of the galaxy, because our whole galaxy is about 100,000 light years wide. But one other thing that you'll notice is that the picture looks kind of grainy. And Theo had mentioned this before when she was talking about her image of the ET cluster. Because this is not a very long exposure image, and when I say a long exposure image, I mean some of these really gorgeous images that you see professional or amateur astronomers put out, they can literally be tens of hours of exposure time together. This is literally 1 minute. So this is pretty darn good for 1 minute to be able to see some of the structure in here. We see a lot of the glowing gas here, and we also see some darker regions here. So these are actually regions where the material is much denser, but there's a lot of dust in there. And so the dust is really good at blocking out visible light. Now I'm going to switch over and show you a professional image of this nebula. Let me switch over. Give me 1 second here and pull this image up. And let me do a new share. There we are there. So this is a really gorgeous nebula. Now, this was taken by a 2.2 meter telescope down in Chile, it's not, I don't believe it's in the Atacama Desert, but it's pretty darn close to it. So we're high up on a mountaintop, so we're getting above a lot of the atmosphere. So the atmosphere, the closer you get to the surface of the Earth, the thicker it is. So even just going a couple of miles up, like onto the top of a decently tall mountain, will get you above a lot of that atmosphere, which tends to scatter out some of that light. It creates that waviness that we saw, like when Adam was showing us Mars, we could really see the waviness being caused by the atmosphere. So views like this are obtained by especially larger telescopes in these much drier, higher up areas. Now, amateur astronomers can get images of this quality as well. It just takes typically a lot more exposure time to be able to pick up some of those finer details. But what we saw kind of over in that first image that I was showing you were these areas where we had a lot of dust right down in here. There's some dust up in here and dust up in here. But a lot of the stars that you see, especially these brighter blue stars, those would have formed out of this gas and dust. And even now you can sort of see how this nebula looks like it's kind of being blown out this way and up this way. And again, that's by these hot stars turning on and pushing that material away through particles that they emit called a solar wind, or merely through the light that they emit. Light actually exerts a pressure. It's called radiation pressure. But I do want to focus in on this area, and to me, this is why I see it as being called the Eagle Nebula, because I can kind of see kind of like I think of it as like the body of the eagle here. Here's the head, and we've got the wing coming up here, and he's got his leg coming down here, and maybe it's kind of like one of these eagles that's swooped down over a river or stream and has picked out a fish and is carrying it off here. So, you know, like Theo was saying, you can make all sorts of shapes out of this. Some people may not even see an eagle in it. But I want to give you one other view. And this is a much closer in view of that little eagle area that I was mentioning just before. So this was this is the second version of a very iconic image that was put out by the Space Telescope Science Institute about 20 years ago. So on the left side here, we see that central portion of the Eagle Nebula. And this was a view taken in 2015. Actually, I think it was the 20th anniversary of the previous image. But this version was taken in 2015 by the Hubble Space Telescope. And the color the light that we're looking in is visible light, the kind of light that your eye could actually see. So if you had enormous eyeballs, like, you know, the size of beach balls, and you were in really dark locations and your eye was incredibly sensitive, and you looked into a telescope, you might be able to see something like this. Now, one major thing that you'll notice is that this view doesn't have that nice red view that we saw before. And so in this view, the individual colors are not what we would consider the true colors, what we would see by eye, if you will. These colors are actually assigned to the light that is given off by different elements. And so in the view that we're seeing here, all of these different colors are basically representative of different elements. Typically, the blue is assigned to be oxygen, red is assigned to be hydrogen, and green is assigned to be hydrogen, and red is assigned to be the light emitted from sulfur. So as Jeremy was talking about, atoms emit their own patterns and colors of light. So no two atoms will emit a single color of light that is the same with another atom. And so if we observe a nebula like this with a filter on our telescope that only lets through the light one very, very particular color of, say, red, then only the light from hydrogen would get through that filter and go into our image. Or maybe the red from sulfur, if we had a different filter, would go through and form our image. So this is what we would call a false color image. Now, the other thing is, so this is visible light. This is the same field of view, and again, it's taken by the Hubble Space Telescope, but now we're looking at a light that is so red that we cannot actually see it. It's what we call infrared. You can detect some infrared light. You feel it as heat. But this is light that has waves that are so long that your eye cannot detect them. And why do astronomers want to look at infrared? Well, as you see now, we can see a totally different view. In fact, the dust is really good that we see over here. This dust is really good at blocking out visible light. Notice that you don't see very many stars through here. But when we look at it in infrared, now the light from the infrared light from the stars, it just goes right through that dust. And now we're able to see those stars. And so Hubble, being able to look in the infrared, is now able to see into these clouds and see what's going on. These are actually areas where stars are forming. You notice up in this section right up here, we've got what kind of look like glowing wisps coming out. That's actually light that is pushing out gas here. So there are stars that are in the process of forming and throughout this cloud, actually. And so they use up that material to form themselves. They won't use it all, But once they start getting big and they start producing a lot of energy, they will then blow away a lot of that gas and dust. And so go forward about 10, 20 million years from now, you wouldn't see the Eagle Nebula like we see in this view here. This gas would be pretty much blown away. And so then you would just see a big cluster of stars there. So again, this is another one of these Messier objects named after Charles Messier, who was a comet hunter from the late 1700s to the early 1800s. And he was searching the skies looking for comets, faint fuzzy objects. And he kept coming across things like the Eagle Nebula. And he couldn't really tell what it was. He had a small telescope, and it wasn't nearly as good of quality as what we have today. And so he just noticed that these objects were faint and fuzzy. So he'd make a note of where they were, and then a few nights later, he'd come back to them and see if they'd moved. And if they hadn't moved, he knew they couldn't be a comet. So this was basically a list of objects, about 110 that he's put together, or that he had put together to say, oh, if I come across one of these things and it's on my list, I know it's not a comet and I can save time and move on. So we've seen a lot of those objects like M17, M20, M8 that Jeremy showed us. Theo had mentioned the Andromeda Galaxy, which is M31. So we'll be visiting a lot more of these in the future as well. So with that, we are running out of time here, and I would like to turn it over to some questions here. It looks like we've got a couple. Let's see. One question is, how large of a telescope would you need to see the structure of a nebula like this? I've viewed some of these objects through telescopes that were about 16 to 20 inches. You can start to see a little bit of the gas, but you can't see a whole lot of the structure. You typically wouldn't see, like, for example, in the Eagle Nebula, you wouldn't see some of these features over here, but you might be able to see that there's this bright glowing area, and you notice that it's kind of dark through here, but you're not going to be able to see a lot of these very fine structures. One of the best objects to look at to try to see structure is the Orion Nebula. It's basically like this, but it's about, something like 5 times closer. It's easy to spot. It's if you think of the sword of Orion hanging down from the belt of Orion, it's what looks like the middle star of the sword. Look at it with binoculars, you'll see that it looks fuzzy, and that's that nebula. Now, even though that nebula is mostly hydrogen gas, just like this nebula and essentially all of these star-forming nebulae, you'll notice that in the Orion Nebula, you might see a little bit of a greenish color. That nebula, especially in bigger telescopes, is bright enough that there's enough green light. It's actually coming from oxygen. There's enough green light that it can start to stimulate the cones in your eye, those color receptors, but the ones that are sensitive to green. There's just not enough of that red light to stimulate the red cones in your eye. But if you took a long exposure image of the Orion Nebula, you would see that it has a lot of that red in it as well. And one final question for me, let's see, what is nebula dust made out of? So this dust, it can be made out of a bunch of different types of molecules that are starting to basically stick together. There are certain molecules called silicates, which have silicon in them and other elements that bond together to form these chains of molecules. And those chains start clumping together, then you get these very, very fine dust particles. Now, when I say dust, I don't mean the kind of stuff like if you take your finger and go over your table. Those dust particles are much larger than what you find in space. So we're talking about dust particles like what's in smoke soot. Okay, so if you've ever watched, if you've seen a cigarette kind of smoking, you'll often see that it has kind of a blue tinge to it. And that's because the particles are so tiny in that smoke that it tends to scatter that blue light just in one of those, like in those reflection nebulae, like in the Triford Nebula. And also I mentioned one final thing, when we talk about dust being a lot denser in here, that's relatively speaking. The densest dust clouds that we're going to find in space are as dense as the best vacuums that we can create in labs here on the Earth. So the densest clouds that we find in space are about 1 billion times, and I'm not just throwing that number up, it's actually, you can calculate it, about 1 billion, B with a billion, times less dense than the air that you're breathing right now. And that's about the limit to what we can create in a vacuum in a lab. So then you think about, well, even the very low density regions, those are even much less dense, especially when you get to space between stars. So with that, I'm gonna turn my light back on here so we can at least see me just a little bit here. And I think, see, yes, I was actually the last presenter. So I guess we could open it up to some follow-up questions to any of our presenters, and you know, go for about, say, 10, 15 minutes or so. So unfortunately, earlier I accidentally dropped out. I think I have a short in my Ethernet cable, so we are still getting some questions together here. But you know, if there are any other questions or some that we didn't answer earlier, something that you just thought of from a previous presentation, then you know, please post those.
Hey, Billy, I'll make one comment while we're waiting for questions to come in.
Yes.
I own a 20-inch Dobsonian, took it out to a dark sky site, looked at M16, the Eagle Nebula, and I basically could not see any structure, including the pillars of creation. So you kind of have to know the stars and the pattern that they form in that object to know that you're actually looking at it. So, you know, other objects like M17, the Omega Nebula that we looked at last time, and then also M8, the Lagoon, M20, the Triford. Those are actually much better telescopic and even binocular targets as far as being able to identify what you're looking at than M16. It's a little hard to really see the structure without a big mirror, so to speak. And then also your point about the Orion Nebula, I can't emphasize that enough. You have to see the Orion Nebula if you haven't seen it, either through binocular, a low power telescope. It will just blow you away. M42, you can see it naked eye, but when you see it through the eyepiece of a telescope, it just is really incredible. You see structure. It's the most spectacular nebula you will see through the eyepiece of a telescope.
Yeah, I would definitely agree with that. And yeah, I've seen the Orion Nebula through, I think it was a 20-inch telescope. It was a 20-inch Dob. And there was enough light there where I could definitely tell there was a little bit of a green glow to it. Most of these objects, to me, they look kind of gray, but this was definitely something where I was starting to see a little bit of that green hue. And again, like I mentioned, that was because of oxygen actually glowing. And it turns out that your eye is most sensitive to the green. So it's perfect that oxygen glows this nice green, so then we can actually see it in this nebula. As one of our research faculty, Dr. Bob Odell, likes to say, nature has been very kind to us.
Mm-hmm.
Let's see, Alex or Nathan, were there any other questions that were coming in? Oh, so there was a question about what are the pillars of creation. So let me share my screen one more time. That is a name that is often given to those particular those big pillars of dust that were in the Eagle Nebula. So these are what we call what has been dubbed the pillars of creation. And so we say, well, why creation? Well, because there are actually stars that are being formed out of this material. And so also when we start looking into these very dusty, dark regions, you think about stars being some of the hottest objects that you can think of. Our sun is about 10,000 degrees Fahrenheit at its surface, and there are other stars that are, many times hotter than that. It's kind of weird to think that the hottest objects in the galaxy, for example, they actually form or are required to form in some of the very coldest parts of the galaxy. So when you go into some of these dust clouds and some of the really dense dust clouds, the temperature may only be a few tens of Kelvin above absolute zero. And that's required so that there's not a lot of pressure in the gas, and it gives gravity a chance to start collapsing these clouds down to form some of these stars. Let's see. Let's see. Best binoculars. this person is still searching for them. So somebody like to chime in on that?
I'll say a couple things. Oberwerk, Oberwerk, I think. They make a good pair of handheld binoculars that I think are relatively cost effective. I've got a pair. I actually used them in July to look at Comet Neowise. That was the best tool, even better than a telescope for seeing a comet, anything wide field. So I would probably start with those. Again, you can spend as much money on binoculars as you want. My buddy's got a pair of image stabilizing binoculars that has a button on it that you click and it just stabilizes, because you have a real hard time stabilizing the binoculars when you hold them in your hand. But again, those can be not as budget friendly. So if you've had a good year in your business and you have a spouse that doesn't mind if you spend a lot of money, then I would recommend a pair of image stabilizing binoculars.
Yeah, I've had a chance to look through image stabilizing binoculars, and they're really, really nice. But like you said, it'll your wallet will hurt afterwards. But if you're going to use them a lot, then maybe it's worth it. So there was another question. I was thinking about Mars because Elon Musk talks about starting life there, even though it's bad. What would life on Venus be like? So I guess I can start the conversation. It would, as far as we know, it would be hard for life to exist on the surface of Venus. Here on the Earth, we have these things called extremophiles, which can survive bitter cold or temperatures that are past the boiling point of water. They would have a very hard, if not an impossible time on Venus, because the average surface temperature is about 850 degrees, daytime and nighttime. So it's hot enough that you could melt lead on the surface of Venus. Or another analogy is if you had a cup of water and you poured it out, it would evaporate before it hit the ground. The pressure at the surface of Venus is like being under a mile of ocean on the Earth, because the atmosphere of Venus is so incredibly thick. It's also got some really nasty stuff in it, like sulfuric acid clouds. So it's just not a great place to try to place life. But who knows? Maybe this phosphine is an indicator that life is able to develop above some of that. When you start getting up into the upper cloud layers, then the temperatures cool off. So, anybody else?
Venus. I think we need to focus on Mars to have any shot at all. I mean, you would last maybe 1 second if you were teleported to the surface of Venus. The only thing about Venus, maybe if your imagination can go to the second Star Wars movie, Episode 5, The Empire Strikes Back, where you had the Cloud City, Bespin. Maybe it'd be paradise in the atmosphere, but you wouldn't want to live on the surface.
Venus is the cruelest joke in the solar system, right? We named it for the goddess of love and beauty, and it's Hades, really. Yeah.
And another Venus question: would the great pressure on Venus keep the water in liquid form? So, does anybody else want to take it, or I can take it? Doesn't matter.
Well, Venus is bone dry. I mean, correct me if I'm wrong here, but it's not only no water on the surface, but even in the atmosphere, the radiation from the sun would have obliterated the water molecules separating the hydrogen and the oxygen. The hydrogen floats away, and I'm not even sure there's much oxygen in the atmosphere of Venus. It's mostly carbon dioxide. Well, I guess carbon dioxide. So it's bone dry. There's no water on Venus.
But yeah, if we could put water on the surface of Venus, it's just the temperature is just so incredibly high that even the great pressure of the atmosphere above it would not be enough to keep it in liquid form. So we can think about going down to the bottom of the ocean, where I think Dr. Bob had mentioned this. We have these black smokers at the bottom of the ocean, where it's basically a volcanic vent on the ocean floor. The water around it is basically freezing cold, but right up around the black smokers, we have water that is well above the boiling point of water, but the water's still in liquid form. And that's because the overlying layers of the ocean create so much pressure that they keep it in liquid form. So even at the center of the Earth, the core of the Earth is solid, even though it's the hottest part and it's metal, you would think that it would be liquid, but because of the enormous pressure of the overlying layers, it actually forces the inner core of our Earth to stay in solid form. The outer part can stay liquid. It's still hot enough and not as much pressure. But yeah, we really probably would not be able to get water to stay around any time on Venus. Another question about comets. Just wondering how common seeing meteors and comets are. I'm a beginner and I would love to see one of them. Anybody else want to take that one?
I will if no one else will, but I've been speaking too much already.
I was going to say there are typically a visual comet that you can see with your eyeballs once every several years. There are several every year that are not too bad for telescopes. Meteors, you just got to be patient. You go outside and you look up. For my money, the Geminids coming up in mid-December are our best shower, partly because we get pretty good skies a lot of times in the winter months. And this year that we have a good no moon situation. So go outside, you can look up on a calendar when the peak night is. I want to say December 14 to 15, it's somewhere in there. But just go take a hot drink and comfortable chair and lay out and look up, and you will see them. It's just, shower is a bad word. It rarely lives up to that sort of, where it looks like it's actually raining stars, although it has happened. But mostly it's just, it's kind of like watching the fireworks when they're widely spaced apart. You'll see a real bright one go zip, and then you go, yay, very nice. And you wait for the next one. So, but that's kind of what it is. It's a question of perseverance. There's a really great website that a Japanese fellow does, and he does weekly information on bright comets where he lists them by how bright they are. And that's just a really good resource because he also lists things several months out, what's coming up. But I don't think there's anything that would be even vaguely naked eye coming up within the next year unless somebody brand new like Neowise comes in.
Yeah, comets are rare and random. It's really hard to predict when they're going to occur until they get relatively close. I mean, we don't see a great one like Neowise, except maybe every 10 or 15 years. Meteors, if you go to a dark sky site and just stay out there for several hours, we'll pull all-nighters and they'll just appear at random. Now, what's really frustrating is when you're there with your buddy and you're looking at this direction of the sky and he's standing over there, looking over there, and he's like, oh, did you just see that? There was a bright fireball, and you just missed it. And you're like, because I was looking here and it happened right behind me. And inevitably it's going to happen once in a while where somebody sees a bright fireball and the other four people missed it because they were looking the other direction.
Yeah, and I'll just add, like the comets like Neowise, those tend to be what we call very long period comets, or they may be on orbits that are known as unbound orbits, where they're moving too fast when they come around the sun. And since they're moving too fast, they go back out in the solar system, but the sun's gravity is not enough to be able to slow them down and then bring them back around for another pass. And so these comets that come in and have never been in our solar system before, they still got tons and tons of ice and or different types of ices and materials, so that when they come in, they're able to put on a spectacular show. When you have a comet like Halley's Comet, which comes around about every 76 years, it's made repeated passes over the course of the solar system's history. You think about, mankind or humankind has been watching this comet for centuries, and that's only been a few of its passes. So over time, its nucleus, that body that's actually generating this beautiful tail, is getting smaller and smaller and smaller. And so eventually enough time passes and Halley's Comet really won't be observable anymore because it will have sublimated or basically evaporated all of its ice. Let's see, any more questions? I don't see any that are popping up in the chat. So, and we are at 9:45. So is there anything that anybody would like to finish up with? Any final thoughts?
I think we've had a couple of questions about starter scope. I just want to share a couple things there.
Yep.
And this question comes up a lot. What's the best telescope if I want to get started as a beginning astronomer? It's the one that's going to get used. It doesn't really matter the size or the type as long as you use it. One of the biggest tragedies is people think they're interested in the hobby, they buy a telescope, they try it out, and then it ends up in the attic collecting dust. It's really what's right for you. Now, to be more specific, I always recommend a Dobsonian telescope, probably a 6 or 8 inch. I own a 10-inch. I paid about $50 for it used. And it's very versatile. It's got a big enough mirror where you can collect light to look at the deep sky objects, the faint fuzzies that we showed you. It's portable enough where you can transport it easily to a dark sky site. I can put it in the back of my small SUV. I drive a RAV4. It fits in there perfectly. It's very easy to set up. It's basically just 2 steps. You plop the mount down, you put the tube on top, and then you just attach it. It takes maybe a minute or 2. Now I'm oversimplifying it because collimation is kind of the, it's a whole nother thing. You got to do it with Dobsonians, make sure that the mirrors line up. I don't spend a lot of time on collimation. You can set it up, take the top off, put your viewfinder, your Telrad on there, and then you're balling. And so if you're trying out the hobby, if you got maybe a son or daughter that's interested in the hobby, or maybe want to try it out, I would say start with a Dobsonian because it's the best bang for your buck, and it just gives you, I think, the most options. So that would be my recommendation.
And I'll just follow up with that. Don't go, you may have to spend a little bit of money up front, and we're talking maybe a couple $100, but that money, if you take care of the telescope, it will literally last you a lifetime. And that doesn't mean like going out and cleaning the mirrors every week or anything like that. If you take care of the telescope, you really won't ever have to clean the mirrors. And all that really involves is putting the dust cap on, and as you're transporting it, just make sure you don't really bang it on something or really misalign something, which there are ways to realign stuff relatively easily. But don't try to get one of the fancy telescopes, especially if you're just starting out. And when I say fancy, I mean one that is like a go-to telescope. No, I've got a really nice one behind me here, but it's also on a mount that was really expensive. And this really ties into the whole idea of you get what you pay for. There are some cheaper robotic telescopes, and they're good for getting you somewhere where you want to go, but they're typically not going to get you exactly where you want to go, and that often leads to frustration. And what I've told people before as well is, like the Dobsonian, that is one where you literally are just sitting it down on the ground and then you push it around to look at the sky. You learn the sky really well that way. And you can use star maps to figure out where things are. And once you have spent some time, it's kind of like a game. Once you have spent some time and you finally find your object, it's very, very satisfying. This telescope behind me, I could have it will point exactly to what I want to, and it only takes it less than a minute to move around in any part of the sky. I would get really bored after about an hour of just looking at every individual thing. But if I had to actually find it, it's much more satisfying to actually do that. And again, you learn the sky and you get a better appreciation of it. Then you can say, oh, you see that bright star up there? Well, just to the left of it is a really nice nebula. So again, you might put out a little bit of money at the beginning to get a nice telescope, but it'll last you. And then, once you really get used to that and you learn how the sky moves, then you might look at upgrading and doing like a robotic telescope. And again, if you want to get a really nice one, that's going to be costly, but just something to keep in the back of your mind. Any favorite sky watching apps or best weather forecasting apps?
Well, I don't use a lot of apps, but I've heard Stellarium and Sky Safari are probably the 2 best ones. Probably Stellarium #1, Sky Safari #2. Anybody have any experience using those?
Yeah, Stellarium, I use it all the time, especially when I'm looking up coordinates. That's more for like laptops and desktops. I think there is a phone version that works decently well now. There's even a version of it that you can just run in your web browser, so you don't have to install anything. So and I think that one even works on mobile devices, but it's free, has a lot of bells and whistles. I've used things like Starwalk, which is an app. You pay for it, it's a couple bucks, but they're really accurate. And there's a whole bunch of them like that. And so they, as far as I can tell, they're all really good at what they do. So.
Sorry, didn't mean to interrupt.
Oh, I was just,
Go ahead. Sorry, Adam, go ahead.
I was just gonna say that we get questions about astronomy and learning and education. There's a lot of homeschoolers out there too. Stellarium is really good. The software, well, there's a different version for all of the different platforms, so it doesn't matter what computer you have, and it is free. It's easy to use. What's great is that you can change your place on Earth while time is going forward, so you can see how your latitude, your position on Earth changes how you see the apparent motion of the sun going across the sky and things like that, and going into day and night. You can put yourself on the poles or the equator. You know, it's just very simple. It just shows you what's up in the night sky and you're done. You can go to other dates and times and also to look at what's going on, and it will do eclipses. So can't be free.
Pay a little bit. As far as weather apps, I use Astrospheric sometimes, although I've blown some observing calls recently, and one of the guys in my group gave me a link to, well, actually put it here in the chat. It's called aviationweather.gov for weather. I guess it's really good. It actually shows you cloud cover and satellite movement. So anybody have any thoughts on that? I guess it's a really good one.
Yep. Also, just cleardarksky.com. You know, it's the Canadian cloud cover model.
Mhm. Oh, and there was a question about how can I find a dark sky area? I've got a link here. Let me pull it up. Let me zoom out just a bit first. Let me share my screen. All righty, so
Yep.
yeah, okay. So this is light pollution map, all one word, lightpollutionmap.info, and you can enter in your address. So we've got Nashville right here. Can everybody see that all right? Okay.
Yep.
So we got Nashville here, which the redder or the pinker or the whiter, the brighter the area. So obviously this is downtown Nashville, right where this pin is. So you wouldn't want to be down there with the telescope trying to take deep sky images. Right down here in Brentwood, we are actually the Dyer Observatory. We are right about here. So as you can see, we're in still a pretty well light polluted area as well. And of course, if you've got humid weather, that's going to amplify this light pollution issue because the humidity in the air tends to scatter the light very well. So if we had the same setup but we were out in Arizona, then this light pollution map will probably diminish some. But you can put in your address and then zoom out, and any of these blue areas, those are going to be areas that are much darker. It's like over around McMinnville. Montgomeryville Academy, for example, has a telescope out there, which is a pretty dark location. But you'll notice that if we zoom out even more, you go out west, and there are some areas that are basically super dark. So out in the out in the desert regions, you're going to have a lot of dark areas. So this again is lightpollutionmap.info, and you can just enter in your address and see what conditions are like.
Yeah, speaking of out west, a year ago, I had the opportunity to go to the Okie-Tex Star Party in Kenton, Oklahoma. It's in the very northwestern tip of the Oklahoma Panhandle. And you talk about, Jupiter cast a shadow. Albireo was just incredible. You could clearly see the color of the stars in the eyepiece, and I could see color in M27, the Dumbbell Nebula. Those are just amazing skies. I mean, if you can get out to something like that, I would highly recommend it, but it's a 2-day drive, so you do have to pay the price a little bit.
Okay, so let's do one final question. I keep hearing about an area having good seeing. Is that the same as the amount of light pollution? No, you can have a lot of light pollution, but you can have really good seeing. Seeing is a measure of basically how still the atmosphere is. So for example, if we had a double star kind of like Albireo, but there are other double stars that appear even closer together. If you have an area with good seeing, then the atmosphere is very calm above you, and you see those two individual stars right next to one another. But when you have a very turbulent atmosphere, all these different layers of the atmosphere have different temperatures and densities. And as light goes through that, instead of going basically straight, uninhibited, it's bouncing around. And that's why the stars appear to twinkle. So if you've got a night of bad seeing, like we had a decently bad seeing tonight here at the observatory, or like when Adam was viewing Mars, his seeing was really bad, and you could really see how everything was moving around. Jupiter, it looked pretty fuzzy. On a really good seeing night, then Jupiter looks much more crisp. Okay. If you go outside and you look up at the stars, especially like the stars overhead, and you see that they're twinkling a lot, you know right then that your seeing is bad. So light pollution is just the amount of, how hard is it to see faint things, but seeing really tells you more about how sharp a thing's going to be. We've got really bad seeing. Even the moon tends to be blurry in a telescope. You can't get those nice defined craters. All right, well, we are almost at 10 o'clock. Does anybody have any final thoughts before we head off here? All right, well, again, I want to thank everybody who joined us tonight, all of our folks at the McGill University, Bays Mountain Park and Planetarium, Barnard Seaford Astronomical Society, Memphis Astronomical Society, and all the folks here at Vanderbilt Dyer, including Alex and Nathan, who were giving us the questions, and then Brian, who was making sure everything was running correctly going out into the world. So thank you all again. Thanks very much to all of our audience. Sorry, I'm getting choked up here talking about it. Thank you very much to all of you who joined us tonight to do this. And somebody did ask, are we planning on doing this after COVID is done with? And as far as I could tell, I think that we should. So I can't make any promises of how often, but I would definitely like to continue doing something like this. So thanks again, and everybody have a great night.